Today, we present PG3, Policy Guided Planning for Generalized Policy Generation by Ryan, Tom, Aiden, Tomas, and Wesley. We are interested in generalized policy learning, where we commonly face the problem that planning for certain tasks can be slow. And in these cases, it can be advantageous instead to learn a policy to solve these challenging tasks. In particular, we are interested in learning a satisficing policy. Note that this satisficing policy does not necessarily have to be optimal. Rather, we are interested in learning a satisficing policy in the hopes that it is easier to express, write down, and find. Thus, our problem setting is as follows. We are given a PDDL domain with training problems and a planner. And as mentioned previously, our objective is to learn a goal condition policy that is able to generalize across all the test problems for this domain. We do so through a generalized policy search, where we search through the space of candidate policies in the hopes of finding a satisficing one. As shown with the figure on the left of a search tree, each of the nodes represents a candidate policy. Our policy representation is a lifted decision list, which consists of an ordered list of rules. The action determined by our lifted decision list is chosen based on the first applicable rule. A rule is applicable if its state preconditions and goal preconditions are satisfied by the current state and the problem. Given this policy representation, the space of policies in which we must search over is large, and thus when we perform our generalized policy search, a score function or heuristic could benefit it. One such score function is policy evaluation. Policy evaluation works by counting the number of problems a given candidate policy is able to solve. However, we expect this score function to perform poorly when we perform a generalized policy search, as we can have policies that are very close to satisficing, but not yet able to completely solve a problem on its own, but policy evaluation will still score these policies equally bad as others. For example, consider this figure here with the forest domain. In the forest domain, the agent must reach the goal state shown as a star. To do so, the agent may walk across the green trail, climb over the gray rocks, walk across the brown dirt, but may not traverse the blue water. Here, we have a candidate policy that says to simply walk along the green trail. Note that this given candidate policy isn't able to solve the problems, as it isn't able to handle climbing over the gray rocks. However, it is very close to satisficing, as it just needs to handle this one extra case in order to solve the problem shown here. However, policy evaluation, because the given candidate policy is not able to solve the problems, even though it is very close to becoming a satisficing policy, gives it a poor score. Another score function is plan comparison, where a given candidate policy is evaluated based on how closely it agrees with the optimal plan returned by our planner. This may also score certain policies that are close to satisficing poorly, especially if they differ dramatically from the optimal plan returned by our planner. For example, as shown here in the forest domain, we have circles where the given candidate policy disagrees and squares where it agrees. Note that we're still considering the candidate policy of walking along the green trail here. Because the walking along the green trail policy is close to satisficing, we would want to give it a high score. Yet plan comparison, as shown here, decides to walk along the dirt instead, and thus gives it a low score instead. Finally, we propose PG3, which performs plan comparison, but now with policy-guided plans. In policy-guided planning, we still have the primitive actions available as before, but with an additional action now. With this additional action, we are allowed to call or ask the policy what it would do in a given state when planning. Furthermore, we are allowed to ask the policy multiple times in succession within one step of planning what it would do. In other words, the policy is able to undergo multiple transitions from a given state within one step of planning to reach a new state. Intuitively, if a policy is very good or very close to satisficing, it should be able to make significant progress on its own and take us close to the goal state or to the goal state itself. Thus, returning back to the forest domain here, we see that the policy of walking on the green trail is able to make significant progress on its own by walking along the green trail and only needs help occasionally from the planner when climbing over the gray rocks. Thus, PG3 scores this policy favorably. Finally, we find that empirically, PG3 is able to more efficiently learn policies that generalize to our test set compared to policy evaluation, plan comparison, as well as other baselines across several domains.